All right, so today we are going to be talking about exponential functions. So I think you'll be having a little bit better of a time than with rational functions because exponentials we've been doing since Algebra 1, so some of the stuff should be very familiar, and most everything you have at least seen. We're just going to kind of kick it up to a college level notch here. So, data patterns. Linear data has a common difference because it's an arithmetic type pattern, which then turns into the slope of that linear equation. Exponential data does not have a common difference. It has a common ratio because it creates a geometric sequence. That common ratio becomes the base of the power. So we should all know that obviously linear data is y equals mx plus b, and so the common difference becomes the m. When we are talking about exponential data, that is in the form y equals a times b to the x, same format you used in Algebra 1. When we say base of the power, that is this guy, b. So base of the power, not the same as this b, right? It is the base of the power. So there's going to be an exponent that is a variable. That's why they're called exponential functions, because the variable is in the exponent. So parent function, f of x equals b to the x, where b is greater than 0 and not equal to 1. Not equal to 1 because 1 to any power is just 1. So that creates a constant function, not an actual exponential function. There are an infinite number of parent graphs for exponentials because when we change b, that changed the parent graph. However, there is a parent pattern that we will be using based on just b, so it works for any of the parent patterns. When we graph exponentials using transformations, this is our format. So we've been doing a, h, and k for, an eternity, and we've got some of that same stuff going on here. So a controls what it always does. So controls reflection in the x-axis if it's negative, right? Also controls vertical stretch and shrink. Remember that we sometimes say compression instead of shrink. They mean the same thing. So that's what A controls. Remember that what we do to the parent pattern is multiply the y coordinates, because it's vertical, changing, by whatever A is. So even though it may be two transformations, it's one step to the coordinates. So if A is, -5, we're going to multiply all the y coordinates by -5. But that represents both a reflection in the x-axis and a vertical stretch by a factor of 5. So this is what we do to the coordinates. This is what we have for the transformations themselves. C is also a multiplied value. C controls reflection in the x or y-axis. Sorry, we just did x-axis. And that's, of course, if it's negative. And horizontal stretch and shrink. Remember that it is the opposite idea as with vertical. So values bigger than 1 are a compression. Values between 0 and 1 are a stretch, which is the opposite of what is true here. And you can go back and look at your original transformations notes because all that still applies. What do we actually do to the coordinates? We multiply the x coordinates by 1 over c, the reciprocal. And we talked about that very early on with transformations as well, because usually if there's a mistake, it's there because people forget to do the reciprocal. But it has to be the reciprocal if there is a horizontal c value. Remember, c is multiplied. So, and notice also that this is in factored form. So if you have a multiplied and an added or subtracted value, if you want to see the transformations, you've got to put it in factored form. H, again, after factoring, controls the horizontal shift. And what do? We add and or subtract to the x coordinates. Obviously, if we are shifting to the right, that's going to add to the x coordinates. If we're shifting to the left, that's going to subtract from the x coordinates. Finally, K controls vertical shift. And we are going to add and subtract to the y coordinates. All right, so the parent pattern. Again, there are an infinite number of parent patterns. Whatever your B is, that creates a new parent pattern. So 2 to the x, 3 to the x, 4 to the x, those are all different parent graphs. But the parent pattern that you should be using for your original coordinates, the x's are -1, 0, and 1. The y's that correspond with those are 1 over b, 1, and b. All right, so now that we have all of our background info, we're going to look at what we need to be able to do with it. So example 1, determine whether the given function is linear, exponential, or neither. For those that are linear or exponential, find a function that models the data. So here is what I would suggest that you do, is that you would first look to see if it's linear, then look to see if it's exponential. Obviously, if it's neither, then we don't need to find a function, but it can't be both, linear and exponential, so it can only be one. So to determine if something is linear, first check and see what the x's are going up by, right? Because if it's not the same thing, then you're going to have to be a little more careful with what you're doing, because we're testing for a common difference, but the gap between the x's has to be consistent too. So here, if I look for the gap here, I'm doing 3 minus 3 halves. So 3 minus 3 halves, which that's 3 minus 1.5, which is 1.5. So that difference is 3 halves. When I go to the next set, I'm doing 6 minus 3, which is 3. So I already do not have a common difference, which means I don't need to keep testing it. So this is a no, because there's no common difference. If you continue to get the same value, right, the constant rate of change, same slope, then we would say, yes, it's linear. The common difference would be our slope, and then we would look for the y-intercept to write the equation. So because it's not linear, now I'm going to look to see if it could be exponential. So same idea, look at the first two, but instead of subtracting, we divide. So 3 divided by 3 halves, so that's the same as 3 times 2/3, which is 2. So then I do the next one, 6 divided by 3, that's 2, so far so good. 12 divided by 6, yep. 24 divided by 12, yes. So I checked all of them. I got the same ratio. So this is a common ratio of 2. So yes. So exponential is the answer. If you were asked to explain, we would say the data has a common ratio of 2. It didn't ask for that this time, so now I just need to write the equation. So when I am writing an exponential function, I'm naming it g of x because that's what the table says. This a value, when there is no h, k, any of those, that means a is going to end up being the y-intercept, but you can always solve for a. So basically, we would say anytime you were doing this, if you're trying to find the value, it's a times 2 to the x. And so if you're unsure as to what a is, you can always pick any of the points. So, if I wanted to pick 324, 2 to the third times a equals 24, right? So 2 to the third is 8. When I divide both sides by 8, I get a equals 3. But the shortcut is that as long as we're not doing something with shifts, which this type of problem, they're not going to give you something like that, then your a value should be when x is 0 or your y-intercept. So 3 times, and we confirmed it here, the common ratio is the base raised to the x power. So that would be our equation there. All right, next ones. Use the transformations to graph each function, determine domain, range, horizontal asymptote, y-intercept. And so we are going to write out all of the things here. All right, so in this case, our base, our b value, right, is 3. So that means that the parent in this case is this guy. So I am going to write it in ordered pair form as opposed to in a chart because it's easier to apply the transformations. So using what I should know about my parent, I should have -1 and then 1 over b. b is 3, so 1/3. This is our first parent point. Then 0, 1, and then 1b. So 1, 3. So these are the parent points. Now I have to figure out what the transformations are. So when I look at these, I do not see parentheses around my 3, which means that the a here is -1. So there's no other number there. It's just the negative by the base. So a is -1. I also have h is -1, right? That's a left shift. And then I have k equals 3. So that means if I were asked to actually list the transformations, what is happening here is a reflection in the x-axis, a shift left 1, and up 3. Because again, sometimes you have a choice as to how you want to show work on transformations. So I'm going to do the coordinates here, but you could graph all of the stages if you so desired. So remember that multiplied changes should be happening before addition and subtraction. So reflection in the x-axis, the a, I multiply times -1 on the y-coordinates. Then left 1 means I'm going to subtract 1 from the x-coordinates. And up 3 means I'm then going to add 3 after I've multiplied to the y coordinates. So the transformation, when I perform those, -1 minus 1 is -2. 1/3 times -1 is -1/3. Plus 3 is 2 2/3, or 8/3. 0 minus 1 is -1. 1 times -1 is -1. Then plus 3 gives me 2. 1 minus 1 is 0. 3 times -1 is -3. Plus 3 is 0. So I've got my transformed. It does not say I have to graph the parent. So if I'm doing, this work, I don't need multiple graphs. I can just have the answer unless it specifically asks for it. So when I plot those points, I have -2 and 2 2/3, which is right here. Then I have -1, 2 and 0, 0. If you do not remember what your exponential graphs look like, by default, the parent graphs look something like this. And they have a y-intercept at 0, 1, right? All the parent graphs do. They also have a horizontal asymptote at y equals 0. So the horizontal asymptote changes when I have a vertical shift up or down. So I do have that this time, up 3. So as you could see by the points that we graphed, my horizontal asymptote should be right here at y equals 3. Because of the reflection, things got flipped. They also can go this way, right? Depends on if it's exponential growth or decay, meaning whether that b is a fraction or whether it's a whole number. So this one, because it's a whole number, would have been the growth version, but then we flipped it. So now this is what my graph looks like. I've got my 3 exact points. I've got my asymptote, so that's all I need for the graph. Now I just need to fill in those key features. So domain, range, horizontal asymptote, y-intercept. So y-intercept is easy because it happens to be one of the points. But again, if it's not, remember, you can plug in 0 for x in the function to get that value. So domain is -infinity to infinity. All exponential functions, it should be -infinity to infinity on the domain unless it's a word problem. The range, in this case, goes from -infinity up to the asymptote. So -infinity to 3 in this case. The horizontal asymptote, we already graphed it, but the equation, again, it is an equation. Don't forget the y equals. And then my y-intercept is at the origin. So here are all of my key features, and there is my graph. So when we are dealing with exponential functions, again, the horizontal asymptote is always going to be at y equals k. Whatever that k value is, that's going to give us our horizontal asymptote. This time my base is e. E, the number, you have that button on your calculator, by the way. E is approximately 2.71, but there is an e and an e to the x button on your graphing calculator. So when I look at this, I don't have an a value. So a is 1, and that's not a transformation. I do have a multiplied value up here, so that means I have a c equal to -1. This -2 is a k value because that's representing shifting down. So in words, the transformation here is a reflection in the y-axis, and a shift down 2. So, parent points. Again, just because it's E does not change anything. These are my X's for the parent points. So -1, 0, 1. And again, worst comes to worst, you forgot the parent pattern, plug those values into the equation, right? Which would be the parent equation is y equals e to the x. So you can plug them right in there. So 1 over b. Well, the base is e. So 1 divided by e, you can do that in your calculator. Rounded to the nearest tenth because we certainly can't graph past the tenths place. So 1 over e, when I round it to the nearest tenth, is approximately 0.4. So we'll put that there. Then it's always 0, 1. And then this is going to be e. Again, I need to be able to graph, so I'm going to write to the tenths place, which e to the tenths place is 2.7. Now I apply my transformations. So my transformations, c of -1, means that I am going to multiply the x coordinates by -1. A k of -2 means that I'm going to subtract from the y coordinates. So -2, -2, -2. Apply both those transformations. So this becomes +1. 0.4 minus 2 is -1.6. This stays 0. 1 minus 2 is -1. This gives me -1. This now is going to give me 0.7. So I've got my transformed points. Again, I should know that because I've shifted down 2, that is going to shift my horizontal asymptote that direction. If there is no k value, then it stays at y equals 0. But here it's going to shift. I plot these points. So 1, -1.6. Then I have 0, -1, and -1.7. So here are my points. And there is my graph. So key features, domain, again, unless it's a word problem that restricts for real life, the domain is -infinity to infinity. In this case, the points are above the horizontal asymptote. So instead of -infinity to asymptote, it's asymptote to infinity. The horizontal asymptote we said is y equals -2. And the y-intercept, which happened again to be one of my points, is 0, -1. Again, if the y-intercept is not one of the points, then simply plug in 0 for x and simplify in your equation. So there are our graphs. All right, so graphing using transformations is part of it. The other part of it is solving some exponential equations. It does say show all the steps. Please, please, please do not skip steps and just have mathemagic happening. I need to be able to see what you are doing. So, our first strategy is going to be to first make the bases match. So, I've got a base of 8 and a base of 16. 16 is not a power of 8. So I can't make it base 8. I need to change them to a smaller number that they are both exponents of. So if you need to check things on your calculator and you don't just know, that's fine. But 8 and 16 are both powers of 2. So I need to rewrite 8 and rewrite 16 as a power of 2. So 8 is 2 to the third power. 16 is 2 to the fourth power. So I have literally kept the exponents the same. All I did was swap out 2 cubed for 8 and 2 to the fourth for 16, which is allowed because they're equivalent. Now I apply my exponent rules from way back when. When you have power of a power, you multiply the exponents. So I'm going to distribute that 3 through. So negative 3x plus 33. Here, same idea, doing 4 times 2x. So that'd be 2 to the 8x. When the bases match, that means that you can then drop the bases. So make the bases match, simplify, then drop the bases. Set the exponents equal. So negative 3x plus 33 equals 8x. And now we're going to solve. So add 3x to both sides. 33 equals 11x. Divide by 11, and x equals 3 is our solution. You can test it if you would like. Negative 3 plus 11 is 8. So 8 to the 8th power. And then this would be 16 to the 6th power. So you can test those in your calculator to see and make sure that you have gotten the right answer. If you think you may have made a mistake, that would catch it if it doesn't obviously work in the equation. So I made a mistake here when I typed this. I didn't have the equation editor, and I couldn't get, this is supposed to be a squared, x squared. So make sure that you write that in there so when you go back to look, you won't be confused. But this is a different type of solving an exponential equation. Sometimes the bases will already match, and you can just drop them and set them equal. You might not even have more than one step on some of them, but these are obviously some of the more tricky things that you might encounter. Also, I find that sometimes in this section, people forget about negative exponents. So if you have, you know, a base of 1/2, for instance, and, you know, somewhere else you have a base of 8, like over here, 1/2 is 2 to the negative first, right? So this wasn't in our problem, but I find that sometimes people forget about the fractions and the negative exponent rule, which is important. So anyway, we don't need that for this problem, but just a reminder to you that that is a thing. All right, on this problem, first I need to apply that exponent power of a power rule. And so then I've got times e to the x squared equals e to the 12th. So other exponent rules that need to be applied. Here I am multiplying. This is not power of a power. Here I am multiplying powers, and the rule says that I add the exponents. So that means when I add them, they're not like terms, so it's going to look like this. And don't be confused. I can, now that the bases match, do the same thing I did over here when the bases were, you know, 2's. With the e's, they're both base e. I can drop the bases. I can set the exponents equal. Now this is a quadratic equation. I can solve it. So I'm going to move the 12 over, set it equal to 0. Because I knew I was going to be able to factor. If you couldn't factor, then I would probably leave it like this to complete the square, but you could also use the quadratic formula if you wanted. This is x plus 6 times x minus 2. So once I have it factored, then obviously set each factor equal to 0. So x plus 6 equals 0, x minus 2 equals 0, and I get x equals negative 6 and x equals 2. Again, this is going to give me e to the 8th times e to the 4th. So when I add the exponents, 8 plus 4 is indeed 12. So that works when I plug in the 2. When I plug in the negative 6, that gives me e to the negative 24th times e to the 36th. Negative 24 plus 36 is 12. So again, showing you that once you have a solution, if you plug it in, it should work. And in this case, we have 2 solutions that work. Okay, so hopefully this is kind of coming back to you from what you did in Algebra 1 as well as in Algebra 2. So you can check out your list for your practice problems and get started on those.